Hi everyone. In this lecture, we are going to discuss nodal analysis. Nodal analysis is a powerful network solving technique. It is a combination of Ohm's law plus the KCL, the Kirchhoff current law. Both are used in conjunction in this method. Nodal analysis is applicable for lumped linear electrical networks only. It is not applicable for distributed nonlinear electrical networks. Nodal analysis and mesh analysis are independent to each other as the KCL and the KVL are independent to each other. So these are the few features of the nodal analysis. Next we'll see simple node. Simple node is a interconnecting point of two elements or two branches. Principal node or essential node, it is an interconnecting point of three or more elements or branches. See, as you can see in the figure, node A is an interconnecting point of two branches, so it is a simple node, whereas this complete node is a principal node where three elements are interconnected. Similarly, this node is a principal node, this node is a principal node, because here the three elements are connected to that particular node, whereas node D is a simple node. From the figure you can see is that node 1 and node 3 are simple nodes, whereas node 2, node 4 and node 5 are principal nodes. Next, so identifying the principal nodes is the first step in the nodal analysis. So one important note is that while you're solving any network theory problem by using nodal analysis, it is always advisable to reduce the number of principal nodes in a given electrical network, because when you reduce the number of principal nodes in an electrical network, it will reduce the number of nodal equations and the solution will be simpler. So before applying the nodal analysis, if it is possible to reduce the number of principal nodes by network solving techniques like source transformation or star delta transformation, we can always do that and reduce the number of principal nodes. See, in this network you can see here there are three principal nodes that are N0, N1 and N2. So it is a network with three principal nodes. N0 is a reference node. N0 is the reference node for this network. It is a reference node. Always we assign reference node voltage as 0 volts. Reference node voltage as the 0 volts. Understand? Next, steps for nodal analysis. The first step in the nodal analysis is identify the principal nodes in a given electrical network. For example, let us say capital N is the total number of principal nodes present in an electrical network. Next, the second step is identify the reference principal node and assign 0 voltage to it. So out of n principal nodes, one principal node will be the reference node. Identify it and assign 0 voltage to this one. So for the remaining n-1 principal nodes, assign the voltages as voltage variables as V1, V2, dash dash dash, etc. Next, at each of these n-1 principal nodes, apply KCL and express the branch current in terms of nodal voltages, unknown nodal voltages. Then it will form a nodal equation. So at each of these non-reference principal nodes, there will be one nodal equation. So for each principal node, we get one nodal equation. Solving the n-1 nodal equations will give you the n-1 unknown nodal voltages. Next, let us see this example. In this example, you can observe that there are three principal nodes. This is one principal node, this is another principal node, and this is a reference node for which we have assigned a voltage of 0 volt. So for this network, to solve this network completely, how many nodal equations we will get? We will get two nodal equations. Understand? Next, for the above problem, if we apply the KCL at node 1, we can see the usual practice is to assume all the currents are leaving that particular node. Here we can see that I1 is the entering current at node 1 and I2 and I3 are the leaving currents. The unknown nodal voltage is V1. So if you apply the KCL, what you are going to get? I1 is equals to I2 plus I3, and what is the value of I1? I1 is equals to 5. The branch current I2 is given by V1 minus V2 divided by the impedance by the impedance of the branch, that is V1 minus V2 by 4. Next, the branch current I3 is given by, what is the voltage at this point? V1, and the voltage at this point is 0. So the branch current I3 is given by V1 minus 0 divided by 2. Similarly, if you apply the KCL at node 2, here you can see that 10 amperes is the entering current and 5 amperes is the leaving current. 10 amperes is entering current into that particular node, whereas this 5 amperes is the leaving current. So the net entering current will become how much? 5 ampere. So 5 is equals to, again, what is the current flowing in this branch from V2 to V1? That we can write it as V2 minus V1, V2 minus V1 divided by 4, and other current that is flowing in branch 6 ohm resistor branch is given by V2 minus 0 volt divided by 6. So you will get two nodal equations. So if you simplify these equations, you are going to get the two equations, and by solving them you will get the two unknown nodal voltages as V1 is equals to 13.33 volts and V2 is equals to 20 volt. Next we will see one more different cases here. Now we will see nodal analysis with voltage sources between the principal nodes. For example, if a voltage source is connected between a non-reference node and a reference node. So if a voltage source is connected between a non-reference node and reference node, then the non-reference node voltage is equal to the magnitude of voltage source, and the number of unknown non-reference nodes is reduced by 1. See, once a direct voltage source is connected between a non-reference node and a reference node, no longer that non-reference node voltage is unknown, we can directly get that voltage. And the second case that we will encounter is that if the voltage source is connected between two non-reference nodes, then it will form a generalized node or a super node. If there is a voltage source, the voltage source may be a independent source or dependent source, it doesn't matter. But if a voltage source is connected between two non-reference principal nodes, then a super node is formed. How to handle these two situations we'll see with one example. Now you see in this example here, how many principal nodes are there at first? See, there are 4 principal nodes, out of which one is the reference node. This is V0 is equals to 0 volts. So already we know the reference voltage. Then how? And you can see here at node 1, a direct voltage source is connected between a node 1 and node 0. Node 1 and node 0. So directly you can get the V1 value is how much? The V1 value is directly, you can obtain it as 10 volt. Understand? So when a direct voltage source is connected between one non-reference principal node and the reference principal node, no longer that principal node voltage is unknown, we can directly calculate that principal node voltage as in this case as V1 is equals to 10 volt. Now you see another point here, V2 is a principal node and V3 is a principal node whose voltages are unknown. So if a voltage source is connected between two unknown principal nodes, then it will become a super node as shown in the figure. It will become a super node as shown in the figure. Why it is called super node? We will see in the next slide. Now you see the current flowing through this 5 volt source from V2 to V3, I am assigning it value of variable Ix. The current flowing from V2 to V3 through this 5 volt source. Because it is unknown, I am assigning the variable Ix. Similarly, the current flowing from the node from V3 to V2 through that 5 volt source, it will become what? Minus Ix. So if we add these two currents, what it will become? It will become 0. It will become 0. So you can neglect the branch current that is flowing through this ideal voltage source in either direction, and you can apply the nodal analysis at V2 and V3, neglecting this particular branch. That is called super node analysis. Now you see, by applying the KCL at node 2 and node 3, what you are going to get? You can see at node 2, what are the currents? I1 plus I2 plus Ix, that is equals to 0. At node 2, if you apply KCL, we are going to get I1 plus I2 plus Ix equal to 0. Let us call that equation 1. At node 3, if you apply the KCL, you are going to get this as I3 plus I4 plus minus Ix equal to 0. If you add this equation 1 and 2, you are going to get what? This Ix and minus Ix will get cancelled. You are going to get the equation as I1 plus I2 plus I3 plus I4 is equals to 0. This is a super node equation. This equation is a super node equation. See, it's very simple. You just have to neglect the branch current through that ideal voltage source, through the voltage source that is connected between the two unknown principal node voltages. Next, so we have the super node equation, and one more thing you have to remember: what is the voltage relationship between V2 and V3? V2 is at higher potential than V3. That is, the voltage at V2 is 5 volt greater than V3. This relationship we can write it as V2 minus 5 is equals to V3. Here you can write this equation as V2 is at higher voltage, V2 minus 5 will become the V3. This is one more relationship that will help in solving this equation. Now you got two equations. We are writing the branch currents in terms of the unknown nodal voltages. See, here you can see what is this I1 current. I1 is equals to V2. Already we know what is the value of V1, 10 volts. So V2 minus 10 volts divided by 2 is I1. Next, what is I2? V2 minus 0. V2 minus 0 divided by is I2. Next, similarly, what is I3? I3 is V3 minus 0 divided by 6. And similarly, this is solving this equation. By simplifying this, you are going to get 0.625 V2 plus 5 by 12 V3 is equals to 7.5. And by solving this one, you are going to get the relation V2 minus V3 equal to 5. If you solve these two equations, equation A and B, you are going to get V1 is equals to 9.2 volt, V2 equal to 4.3 volts. And already we know what is the V1. V1 value is equals to 10 volts. So you know all three principal node voltages, and that equation is solved. Thank you.